Heureux d'un printemps qui me chauffe la couenne, triste d'avoir manqué en pauvre hiver. Je peux pas faire autrement, ça me fait de la peine. On vit rien qu'au printemps de quoi longtemps. Après la vie, assis sur le bord de mon trou, je me creuse la tête. Je pense au bonheur des gens, je sais bien que ça va pas durer. Ça prend des sous pour faire la fête. Quand qu'appartient le beau temps, l'hiver, l'été durant. L'été c'est tellement bon quand t'as la chance d'avoir assez d'argent pour voyager sans t'inquiéter. Pour le fils de patron, c'est les vacances. Pour la vie de restaurant, c'est le sueur des clients. Après la on dit que l'hiver est blanc comme un nuage, mais ça évidemment comme chalet près du foyer. Dans le fond, c'est salissant pour risquer le chauffage. Y'a pas pire moment de l'année quand t'es prêt pour t'endetter. Après faut que je m'en retourne à mon trou, creuser ma peine. J'ai vu le surintendant, je peux le dire en attendant. Le jour où ça sera nous qui ferons la fête. Imaginez le printemps quand l'hiver sera vraiment blanc. Qui me chauffe la couenne, triste d'avoir manqué en pauvre hiver. Faire autrement, ça me fait la peine. Et non, rien comme printemps de pas longtemps. Dans le printemps, qui me chauffe la couenne, triste d'avoir manqué en pauvre hiver. Faire autrement, ça me fait la peine. Et non, rien comme printemps de pas longtemps.
How are we doing? Questions while we wait for others to come in? We can have a look at what we were doing last time, right? We introduced or reviewed today's music brought to you by Paul Pichet. The quintessential Quebec artist, I would say. Never had a huge hit with anything. This is one of his best known songs, I think. Heureux d'un printemps. Which I thought was befitting. I mean, it's quite nice out today. Not as sunny as we were forecasting, but nonetheless. Yeah, I mean, to many people, Paul Pichet represents the sound of Quebec. A lot of newer artists are emulating is sound? All right. If A is a proper subset of B, can B also be a proper subset of A? Valid question. The answer is no. No, because if A is a proper subset of B, what does that mean? That means that A is a subset of B, but A is not equal to B. So there have to be some elements of B which are not in A. So there has to be an element of B where little b is not in A, and thus B is not only not a proper subset, but not a subset at all. Because in order for B to be a subset of A, every element in here must also be in there, but we don't have that here. So as Annie suggests, A has strictly less elements than B. Absolutely. Consider this set B here. Here we have a bunch of questions associated with that. True or false? And so on and so on. Let's stop it there. That'll be enough. Right, so true or false? A is an element of B, true or false? Well, I mean, I see it right here. So true. BCD is a proper subset of B. If this was true, then every element in here would have to be an element of B. Is B an element of B? It is. It's right there. Is C an element of B? It is. Right here. What about D? D is not an element of B. The set containing D is an element of B. So this is false. Right? The set containing D is an element of B. It's right here. This is true. The set containing B is a subset of B. If that is true, then every element in here has to be an element of B. The only element here is D. Is D an element of B? It is not. Right? In fact, the set containing D is actually an element of B. And finally, the set containing E and F is an element of B. Is that true? It's right here. You see it. True. How are we doing here? Questions? So F is not an element of B. That's correct. F is not an element of B. What's the difference between E and C? What's the difference between these two things? E and C? Thomas, is that what you meant? F on its own, right, Britton? So F on its own is not an element of B, and neither is the set containing F, right? That's not true either. Thomas. Oh, between these two. So what's the difference between this and this and this? Yes. This is an element of. This is a subset of, and this is a proper subset of. Proper. Why is D false? If D was true, every element in here would have to be an element in here. The elements in this set is D, and D is not an element of B. The set containing D is an element of B, which is why C was true. All right. Let's move on. Last time we introduced the idea of Venn diagrams. And let's use Venn diagrams to prove a few nice things. Kyler wants to re-explain D again. If, in order for this to be true, in order for the set containing B to be a subset of B, all the elements in the set should be in B. Now, the only element is D. Is D an element of B? It is not. The set containing D is an element of B, which is why. Right, we had introduced the idea of Venn diagrams last time, and we showed that we could represent a few sets. Let us use Venn diagrams to get a nice equation for the cardinality of A union B. Right, suppose we have two sets and we wish to ask the question, how many elements in the union? Well, let's start by adding the number of elements in A. And if we add the number of elements in B, you see that a portion has been counted twice. Right? The stuff in here has been counted twice. And what is that? Well, we saw last time that this region was actually the intersection. So if we remove the number of elements in the intersection, then everything will have been counted once. And there you have it. A very nice equation for the number of elements in the union in terms of the number of elements in each set minus the cardinality of the intersection. Can we repeat 3 cents. Can we get a formula for the cardinality of the union of 3 cents? Well, again, let's start by adding the elements in A and adding the elements in B and adding the elements in C. Now you see what happens, right? I mean, the elements here have been counted twice, the elements here have been counted twice, the elements here have been counted twice, and the elements here have been shaded in 3 times. Oliver is asking if there's a formula for the cardinality of A intersection B. Well, I mean, you could switch these, and then you would have the intersection in terms of the union. There's no other way to do it just using A and B. Right, so here you see this has been counted twice, 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 and this part right here has been counted 3 times. So let's remove this part once, and that is the intersection of A and B. Let's remove this part, which is the intersection of A and C, and let's remove this part, which is the intersection of B and C. So we've removed this once, and this another time, and this yet a third time. So in fact, we're now missing the stuff right here, which used to have been counted 3 times, has been removed 3 times. So we're not counting that at all. So now we have to add that in, and that is where all 3 sets intersect. A intersection B intersection C. Thank you, Annie. How are we doing? Let's take a few examples from the book. Right, consider this. We have the cardinality of A is 15, cardinality of B is 30, cardinality of the union is 33. How many elements are in the intersection? Well, I mean, we have this nice formula here. Cardinality of A union B is cardinality of A plus cardinality of B minus the cardinality of the intersection. So here, this is 33. This is 15. And 30. Minus the cardinality of the intersection. And there you go. If you interchange these, this is easily seen to be 12. Is that right? Everybody with us? (26), we are given cardinality of A is 28, cardinality of B is 12, cardinality of A union B is 32, and cardinality of A primed is 19. They are asking us to draw a Venn diagram and fill in the information. All right, so draw a Venn diagram and fill in the information. That's the question. And again, it's best to start from the middle and work your way out. So what is the middle here? And again, from the same formula, cardinality of A plus cardinality of B minus cardinality of the intersection. That is 40. So we see that the cardinality of the intersection should be 8. In other words, we have 8 elements, thank you, Annie, in the intersection. But now A has a total of 28 elements. So if there are 28 elements here in total, and you've already got 8 there, then you're missing 20. Similarly, B has a total of 12 elements, but you've already got 8 here. So there are 4 there. And finally, A complement has 19 elements. So outside of A, you have 19 elements. You've already got 4 there, so you are missing 15. And there it is. Convinced? Where did I lose you, Brendan? Right, remember we introduced the notation last time. A prime really means, it's notation for a complement. It's everything in the universe that is not in A. Right, so everything outside of A should be 19. Everything outside of A should be 19. We already have 4 here, so everything else must be 15. Is B a part of A complement? Well, not all of B, right? Because this part is an A. So that's why I'm hiding everything here. So this part is part of A complement. A complement is everything outside of A. B is not equal to 4. This part of B is equal to 4. Everyone, right? This part is equal to 4 because you already had 8 here, and you know that B has a total of 12 elements. Let's try another. Cardinality of A is 54. Cardinality of A intersection B is 22. Everybody with us? Everybody, I think everybody's up to speed. Same question. Same question. Draw a Venn diagram and label every part. All right. Again, it's always best to start from the center and work your way out. The center is the intersection of all 3 parts. The intersection of A, B, and C has 4 elements. The intersection of A and C has 15 elements. Right? So this part, which is the intersection of A and C, has 15 elements. We already have 4 there, so we are missing 11. The intersection of B and C has 16. We already have 4 here, so 12 there. C has a total of 44 elements. So in here we have a total of 44 elements. We already have 27 elements. 27 already, total of 44. We are missing 17. Is that correct? 21, 33, 34, 44. Looking good. All right. The intersection of A and B has 22 elements. I've already got 4 here, so I'm missing 18. A has a total of 54 elements. But how many do I have? 29. I've already got 33, so I'm missing 21 elements. Where did the 11 come from? This was the intersection of A and C. The intersection of A and C has 15 elements in total, but we already had 4 in this part, so I was missing 11. 21 is correct, thank you. The number of elements in A union B, if you put together all of this and all of that, you should have 85 elements. But this is already 54. So 54 plus 12, 66. And we want 85, so I think we're missing 19. Is that correct? 19? Anyone? Thank you, Annie. And finally, B complement has 63 elements. So everything outside of this should add to 63. So what do we have here? 7, 8, 9, 2, 3, 4, 49. That's 49 elements. We should have 63. So we're missing 14 elements. 14 outside of that. Is it 24? Have I made a mistake? 2, 3, 4. That's 49. I think it's 14. It's all good? There it is. How are we doing? Questions? Too easy? Yeah, no, I think so. I think it's very easy to understand with Venn diagrams. And now let's use Venn diagrams to prove statements about sets. 19. Where does this 19 come from? We have, what do we have? We have that A union B is 85. So everything in A and everything in B should add to 85. We didn't have the 19 yet, right? So here, these numbers give you all of A. So I mean, you can add them together, but It's easy to see that these act at 54. So this is 54 plus 12 is 66, but you were supposed to have 85. So 66, so 85 minus 66 is 19. You're missing 19. There it is. Is there a limit to the number of sets in Venn diagrams? There is not. There is not, but it becomes messy after 3. Kind of messy. Let us use Venn diagrams to prove statements about sets. Here's the claim. A claim that we actually saw last time. We noticed something when we took a specific example. The complement of A union B is the same as A complement intersection B complement. Let us prove this result using Venn diagrams. Using Venn diagrams, the proof is going to be very easy because we're going to work out the Venn diagram for the set on the left. We're going to work out the Venn diagram for the set on the right, and we're going to observe that they're exactly the same Venn diagram. So let's look at the Venn diagram for A, which is this. We're going to draw the Venn diagram for B. And so now, under these, we can draw the Venn diagram for A union B. Right? When you take the union, it's everything in here coupled with everything in here, or everything as well as everything common to both. So whatever's shaded. This is A union B. Now what do we want? We want the complement of this. And so, if we talk about the complement, A union B complement, as you know, the complement of a set is everything in the universal set that is outside of that set. So the complement of this is everything that is not shaded. So the complement of A union B is everything outside of this shaded region. The complement of A union B is this region right here. All right, so that's the Venn diagram for the left-hand side. Now let's look at the Venn diagrams for the right-hand side. Well, we already have the Venn diagram for A here. So let's draw the Venn diagram for A complement. It's everything in the universal set that is outside of A. So everything that is not shaded. This is A complement. Similarly, B complement right? We have B right here. The complement of B is everything that is outside of B. So everything that is not shaded. So that's B complement. And using those two, let's look at A complement intersection B complement. Now, as you know, the intersection is whatever's common to both. So what is shaded in both of these things? Well, A is not shaded in here, so we're not going to shade it there. B is not shaded in here, so we're not going to shade it there, but everything else is shaded. And there you have it. And you see that these two Venn diagrams are exactly the same. So they represent the same set. How are we doing? You see how simple this proof using Venn diagrams is? You could prove it a different way. You could prove it using properties of sets. And let's do so just for fun, just to see how more complicated it actually is. To prove that these two sets are equal, you have to show that they contain the same elements. To prove directly, you have to show they contain the same elements. Right, that's our definition of when two sets are equal. So let C be an element in here. What does that mean? What does it mean for C to be an element of the complement? Well, it means that C is not in A union B. Right? It means it's outside of A union B. Now, you know what the union means, right? If C was in any of these, then C would be in the union. So if C is not in A union B, then C is not in A, and C is not in B. But if C is not in A, then C is an A complement. So if C is not an A, then C is an A complement. And similarly, C is a B complement. So C has to be in the intersection of the two, right? Because it's in both of these. So it's going to be in the intersection. So what have we done? We have shown that if C is an element in here, then it had to be an element of here. In other words, that A union B complement is a subset of A complement intersection B complement. And then you need to prove the converse. Take an element in here and show that it's in there. Let's not do it, but that would only be half of it. You'd have to show the other half as well. I think Venn diagrams are a lot easier than doing it from sets in general. When two sets are equal, they will be subsets of each other. Exactly, right? One set is a subset of the other, and vice versa. Absolutely. So this thing that we proved is actually 1/2 of De Morgan's laws. So De Morgan's laws. The complement of A union B is A complement intersection B complement, and the complement of the intersection is the union of the complements. I'll let you prove the second one using Venn diagrams. Let's prove this one here. In this case, C is also a part of the union of A complement and B complement. For the second one here, absolutely. So, I mean, of course you can prove it using that second approach. Yeah, so I mean, you have two options, either the second approach or Venn diagrams. I think you want union instead? Absolutely, that would be correct. That would be correct. But that's not what we're working towards, right? We're actually working towards the intersection. So you're right that it's also true for the union, but that won't help us in that particular case. Consider this. A distributive property of union, right? You can distribute, distributive property of union. That's what it's called. Let's prove it using Venn diagrams. Well, once you have a little bit of experience, you don't have to write everything in complete detail. Let's draw the Venn diagram for A. This is it. Let's do B intersection C. Right, you don't have to do B and C separately and then the intersection. I think we all know what the intersection of B and C are. It's whatever's common to both B and C. This stuff right here. If you're not comfortable with that, then you really should do it step by step. But I think everybody's fairly comfortable with that. And now, if you put the two together, the union is whatever's shaded. So this whole thing is shaded. And so is this. So all of that and all of this. Convinced? Now let's do the right-hand side. A union B, you know what that is. Whatever's in A and whatever's in B together, we saw that already. A union C and now if we look at the intersection of those, right, whatever's common to both of these shadings, right? That's what the intersection means. It has to be in both of them. So we certainly have all of A here and this little sliver as well. So all of A and that sliver. Exactly what we had before. How are we doing here? consider the following. Most mathematics professors love to invest their hard-earned money. A recent survey of 150 math professors revealed that 111 invested in stocks, 98 invested in bonds, 100 invested in certificates of deposit, 80 invested in stocks and bonds, 83 invested in bonds and certificates, 85 invested in stocks and certificates, and finally 9 did not invest in any of the three. How many mathematics professors invested in stocks and bonds and certificates of deposit? So the question is, how many invested in all three? I think we're missing one crucial piece of information. There were 150 surveyed. Let's draw a Venn diagram of what's happening here. So stocks, bonds, and certificates of deposit. What do we want to know? How many invested in all three? And as I suggested, when you're filling these out, you really want to start from the middle and work your way out. And the middle is exactly what the question is asking. How many invested in all three? So we don't know. Let's call it X. We don't know how many people invested in all three. That's in fact the question they're asking. But 80 invested in stocks and bonds. So all of this is 80. So if we already have X here, this should be 80 minus X. Minus X. And 83 people invested in stocks and certificates. So if we have X here, this should be 83 minus X. And 85 people invested in stocks and certificates. So this should be 85 minus X. All right. 100 people total invested in certificates. So all of this should add up to 100. What does it add up to? This is 83. 83 plus 85 is 168. 168 minus x. So this should be 100 minus 168 minus x, or x minus 68. Similarly, this, you've got 111 total. If you add these, that is 80 plus 85, that's 165. So that's 165 minus x. And you want 111, so it's 111 minus this, or 54, x minus 54. And finally, for bonds, this is 83. Plus 80 is 163 minus x. So this is x minus 65. And finally, we know that 9 did not invest in any of the three. So there you have it. And there were 150 people surveyed. So if you add everything up, that should give you 150. So immediately, this is 111. And then plus this, plus that, plus this, plus 9, that should give you 150. What does it give you? The x's cancel here. This is 120 plus x minus 65 plus 83 minus 68. So that is 55. 55, so that's minus 13. That is 70. So x is easily seen to be 80. $80 invested in all three. All right. How are we doing? Moving on. Let's move on to the fundamentals of probability. Let's start by defining some terms which we'll use over and over again in our study of probability. Definition. An experiment is an activity or occurrence with an observable result. Each repetition of an experiment is called a trial. The possible results of each trial are called the outcomes with an observable result. The possible results of each trial are called the outcomes. The set of all possible outcomes is called the sample space. Let's illustrate these with a few examples. The question is asking us to write a sample space for the following experiment. Number 4, a day in April is selected for a bicycle race. So a day in April is selected for a race. What is the sample space? As you know, there are 30 days in April. So the sample space could be the set of numbers 1 to 30. Number 6, A person is asked the number of hours he or she watched TV yesterday to the nearest hour. So how many hours can a person have watched TV yesterday? Right? What is the sample space? Well, I mean, it's possible that he or she did not watch any TV, so maybe 0, all the way to 24. Right? So the experiment would be asking somebody how many hours he or she watched TV. Each time you repeat that, you get a new trial. And the answer, the outcome, is going to be one of these numbers, 0 to 24. Eight rather. A record is kept each day for 3 days about whether a certain stock goes up or down. What's the sample space? What's the sample space? What are the possible outcomes? How would you define, how would you describe a sample space to illustrate what's happening here? Of course, if the stock is GME, I mean, it's always up. So. But here, what can happen? Well, I mean, it could be up, up, up. Up, up, down. Up, down, up. Up, down, down. Down, up, up. Down, up, down. Down, down, up. Down, down, down. Yeah, exactly. To the moon. Good point, Brendan. It could, it might not move. So that's a valid point. It's a valid point. I guess to be fair, we should have considered that. We should have thrown an even in there. Let's not do that. Let's not do that. And let's throw in, if it doesn't move with the up or with the down, it really doesn't matter. but a valid point nonetheless. All right, let's do one more. Number 10, a box contains 5 balls numbered 1, 2, 3, 4, 5. A ball is drawn at random, the number on it recorded, and the ball is replaced. The box is shaken, a second ball is drawn, and the number is recorded. So you understand the scenario, of course. You've got a box with balls. Balls numbered 1 through 5. You pick a ball at random, record the number, put it back, mix it up again, and draw a second ball whose number you also record. What is the sample space? What are the possible outcomes? What can happen here? Well, you could draw one, put it back, and draw one again. So maybe 1, 1, or 1, 2, or 1, 3, 1, 4, 1, 5. Maybe you start by drawing 2, 1, and 2, 2, all the way to 2, 5, and so on and so on. 5, 1, 5, 2, all the way to 5, 5. And as Annie suggests, you will have 25 elements in the sample space. Absolutely. Definition: an event. Number of options, so the number of times, absolutely, yeah. So if you wanted to count them, the question wasn't asking, and Annie answered a question that did not come up, but both of you are correct. 25 elements, absolutely. An event is a subset of the sample space. An event is a subset of the sample space. Take an example. Suppose that you have a 52 card deck. For those of you unfamiliar with the regular 52 card deck, you have aces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a jack, a queen, and a king. In 4 suits: hearts, diamonds, clubs, and spades. So 13 times 4, 52. Suppose you're asked to pick a card at random. Pick a card. What's the sample space? Well, There are certain variations you can play around with for the sample space. First, you could list absolutely all the cards that you wanted. Ace of hearts, two of hearts, three of hearts, all the way to king of hearts. Ace of diamonds, two of diamonds, three of diamonds, all the way to king of diamonds, and so on and so on. So 52 cards you could list for the sample space. Or you could have ace, 2, 3, 10, jack, queen, king. It depends very much what the situation actually is. This could be enough. This might not be enough. In this case, if I define the event as drawing, so let E be the event that you draw a face card. And what do we mean by face card? We mean a card that has a face on it. In other words, either a jack, queen, or king. That's your event. The event is drawing a jack, queen, or king, and that event is a subset of the sample space. Let's take another example. Suppose an experiment is that you flip a coin and roll a die. What is the sample space? Right? Let's work out a sample space for this experiment. What are the possible outcomes? Well, you're flipping a coin, so it's either going to be heads or tails. And you're rolling a die. I am assuming a 6-sided die here. So you're either going to roll 1, 2, 3, 4, 5, or 6. So what are the possibilities? Either heads 1, heads 2, heads 3, heads 4, heads 5, or heads 6. 1 to 6 for the die, heads or tails for the coin. So heads 1 all the way to head 6, or tails 1 all the way to tails 6. This is your sample space. Let E be the event that you roll a 4. If E is the event that you roll a 4, what is E? As a subset of the sample space. Well, I mean, you don't know what you flipped. It could have been heads, but for sure you rolled a 4, so heads 4 or tails 4, which is a subset of the sample space. All of this is trivial stuff, of course, But in a moment, thank you, Annie. And by a moment, I mean next week, we're going to throw in probability to these things. Are they proper subsets? They are proper, but as you know, they are also subsets as well. Right? 6 is less than or equal to 7. That's true. I mean, you know more, right? You know that 6 is strictly less than 7, but this is also true. And it's the same thing with subsets versus proper subsets. Will matrices come into play with probability? Not in this course. Yeah. So the stuff we did before the midterm is completely independent from the stuff after. The sample includes other elements that the event of rolling 4 does. Absolutely. Absolutely. Right? I mean, the obvious question that's going to come up is, what is the probability of event E occurring? And next week, we're going to see how to calculate these probabilities. So all of this, very easy stuff. It's just the rudimentary beginnings of probability. But starting next week, we'll put all of this together. We'll put this to good use and define the probability of an event. Thank you all for coming, folks. You guys have a good weekend, and I will see you on Tuesday.